Hello friends, I welcome you in lecture number 12 on series solutions of differential equations. In this lecture we are going to discuss about Frobenius method for finding the solution of this type of ordinary differential equation of second order. We have seen how to obtain the power series solution if we have an ordinary point. Suppose x0 is an ordinary point of the differential equation y double dash plus px into y dash plus qx into y equal to 0, then we know that we have at least one solution in powers of x minus x0, and that method is called power series method. And we have seen enough number of problems of this type in which we have obtained power series solution if x0 is an ordinary point of this type of differential equation. Now suppose x0 is not an ordinary point, then x0 will be a singular point, and we have seen in lecture number 2 on series solutions that there are two types of singular points: regular singular points and irregular singular point. And we are going to discuss the method for regular singular points, and that method was developed by Frobenius. So it is called Frobenius method for finding the power series solution. If x0 is a regular singular point of that differential equation y double dash plus px into y dash plus qx into y equal to 0, then Frobenius method says that equation has at least one solution in this form: x raised to r sigma a n x minus x0 to the power n, where n equal to 0 to infinity. Or we can write in this form also. Here also I will write x minus x0, and this I can rewrite as sigma a n x minus x0 to the power n plus r, where n equal to 0 to infinity. Here r is any real number or any complex number. So if x0 is a regular singular point of the differential equation y double dash plus py dash plus qy equal to 0, then Frobenius method says that there exists at least one series solution which can be represented in this form, where r is any real or complex number, and we will discuss how to obtain values of r for this solution. So this is the idea of the Frobenius method, and Frobenius method says that power series solution will be in this form, where we have to determine these constants a n that we can determine by substituting this solution in the given equation and by comparing the coefficients of like powers of x. So the idea is same. First we check whether x0 is a regular singular point or not. If x0 is a regular singular point, then we will start by assuming the solution in this form, and then we will substitute value of y, y dash and y double dash in the given equation, and we will try to determine these constants a n. Here new thing is this power r. So we will decide the values of r also, but that I will discuss with the help of example. It is not easy to discuss about this quantity r directly. That we will understand while we are doing one problem related to this Frobenius method. Now suppose x0 is 0, then our solution will look like this: y equal to x raised to r sigma a n x raised to n equal to 0 to infinity. Or I can rewrite in this form also: sigma a n x raised to n plus r n equal to 0 to infinity. and generally they ask for the ordinary or regular singular point for x0 equal to 0. So we will be using this form of solution if we have x equal to 0 as a regular singular point, and we have to decide this value of r and these coefficients. So with this in mind, we try to solve one problem related to this Frobenius method. So I have taken this differential equation, and here you are asked to find a Frobenius series solution of the differential equation 2x square y double dash plus x y dash minus x plus 1 y equal to 0. This question was asked 2 times in GTU Summer 2019 as well as Summer 2020, and they have not specified that about which point we have to decide the Frobenius solution. So if point is not specified, we will consider our point as 0. So first we have to decide whether x equal to 0 is a regular singular point of this equation or not. Then only we can apply this Frobenius method. So for that we have to write our equation in this standard form: y double dash plus px into y dash plus qx into y equal to 0. That is, coefficient of y double dash must be 1. Here it is 2x square. Therefore first I have to divide this whole equation by 2x square, and then I will compare the resulting equation with this standard form. So I have divided this equation number 1 by 2x square, and we have y double dash plus x divided by 2x square, that is 1 by 2x, minus x plus 1 divided by 2x square y equal to 0. And if we compare this differential equation with y double dash plus px into y dash plus qx into y equal to 0, we can see that this is our px and this is our qx. Px is 1 by 2x and qx is minus x plus 1 over 2x square. And to check whether x equal to 0 is a regular singular point, we have to find out whether x times px and x square times qx are analytic at x equal to 0 or not. If both are analytic at x equal to 0, then x equal to 0 is a regular singular point. So I have multiplied this px by x, and I have 1 by 2, and I multiply this by x square. So x square will cancel out and I have x plus 1 by 2. And it is clear that this function 1 by 2 and x plus 1 by 2 both are analytic at x equal to 0. Therefore x equal to 0 is a regular singular point of equation number 1, and therefore we can assume that Frobenius method applies. So by Frobenius method we can say that there exists at least one solution of given equation of the form y equal to x to the power r sigma an x raised to n equal to 0 to infinity. And here we assume that a0 is not equal to 0. So why we are assuming a0 not equal to 0, that we will discuss as we proceed further. And this I can rewrite in this form also: sigma an x raised to n plus r n equal to 0 to infinity. Now it is clear that this y is a solution of given equation, therefore it will satisfy this equation number 1. And in equation number 1 we have first and second order derivatives, so we have to decide y dash and y double dash. So for that we can rewrite this as, if I consider n equal to 0, I will have a0 into x raised to r. For n equal to 1, I have a1 times x raised to r plus 1. For n equal to 2, I have a2 times x raised to r plus 2, and so on. Now if I take derivative with respect to x, then I will have y dash equal to a0 derivative of x raised to r is r times x raised to r minus 1 plus a1 derivative of x raised to r plus 1 is r plus 1 times x raised to r plus 1 minus 1, that is x raised to r. Similarly, a2 times r plus 2 x raised to r plus 2 minus 1, that is r plus 1, and so on. And if we want to write down this in sigma notation, then you can see this is starting with 0. So I should write n starts from 0 and going up to infinity. And here you can see, if I have r here I have r minus 1, that is you can see derivative of x raised to n plus r is n plus r times x raised to n plus r minus 1. And you can check by putting values of n. If I take n equal to 0, I will have a0 r x raised to r minus 1, that is first term. For n equal to 1, I have a1 r plus 1 x raised to r, then a2 r plus 2 x raised to, if I take n equal to 2, I will have r plus 2 minus 1, that is r plus 1. So I can directly write down derivative, that derivative of x raised to n plus r is n plus r into x raised to n plus r minus 1, and this an constant as it is. And summation is not changing, index is taking the values from 0 to infinity. So that you can see from this, that we have to consider n from 0 to infinity, because our power is starting with x raised to r. If there is no power of x here, if a0 was constant, then we had taken y dash equal to sigma n equal to 1 to infinity. That we have done in the case of this type of solution, sigma n x raised to n equal to 0 to infinity. In this case, we are taking y dash equal to n times an x raised to n minus 1, n is starting from 1 to infinity. But that is not the case here, so be careful. You can directly write down the derivative. Simply write down the derivative of x raised to n plus r, and summation is from 0 to infinity. Similarly, for y double dash, we keep these two terms as it is, they are independent of x, and derivative of x raised to n plus r minus 1 is n plus r minus 1 into x raised to n plus r minus 1 minus 1, that is x raised to n plus r minus 2, and rest of the things as it is. So this is y double dash. Now once we obtain these values, we put them in the given equation, and the given equation is 2x square into y double dash plus x into y dash minus x plus 1 into y equal to 0. So we are substituting values of y double dash, and y in this equation. So that I have done here. 2x square into y double dash x into y dash minus x plus 1 into y equal to 0. In the next step, we can take this inside the summation because it is independent of n, and here power of x is x raised to n plus r minus 2, and I will multiply this by x square. So power will be x raised to n plus r, and these two will be in the product. So that I have written here. If I take this inside the summation, 2 times n plus r minus 1 an x raised to n plus r. Same thing here, we can take this inside and combine with this. This is x to the power 1, so that x to the power 1 will cancel out this minus 1 power, and we will be having x raised to n plus r power only. So that I have written here. Here I will multiply this summation by x as well as 1, and I will take negative sign, and x into this will give me x raised to n plus r plus 1, that is minus an x raised to n plus r plus 1, and minus sigma an x raised to n plus r equal to 0. Now in the next step we have to take care that we have x raised to n plus r in every summation. We will try to convert every summation in this form, something into x raised to n plus r, and if we are not having x raised to n plus r, we will change the index and we will try to obtain x raised to n plus r into something in every summation, so that we can compare the coefficients of like powers of x. So in all these three summations we have x raised to n plus r, but here we don't have x raised to n plus r. Instead of this we have x raised to n plus 1 plus r. So for that we can change this variable n by n plus 1 equal to some new variable. So I have taken n plus 1 equal to m here, and that will give me n equal to m minus 1, and when n will take the value 0, m will start from 1. For n equal to 1 we will have m equal to 2. So if n is from 0 to infinity, m will be from 1 to infinity, and this is going to be x to the power m plus r. This n will be replaced by m minus 1. So I have make change in this summation only, and rest of the summations are as it is. So after changing we will have sigma a suffix m minus 1 x raised to m plus r m equal to 1 to infinity. So that is the only change in that step that I have written here. A m minus 1 x raised to m plus r m equal to 1 to infinity. And now this is dummy index. Instead of m, again I can replace m by n because it is dummy index. So in the next step I have replaced this m by n in this summation, rest of the things as it is. Now after this we can see this is starting from 0, this is also starting from 0, this is also starting from 0, but this is starting from n equal to 1. So we have to write all the summations which are starting from n equal to 0 as term corresponding to n equal to 0 plus sigma n equal to 1 to infinity. Because if I want to combine two summations, then the range of index must be same. So here I will write down the term corresponding to n equal to 0 plus this summation from n equal to 1 to infinity. Similarly here also I will write down the term corresponding to n equal to 0 and plus sigma this quantity from n equal to 1 to infinity, and same thing here. So that work I have done in the next step. If I take n equal to 0 here, I will have 2 into 0 plus r, that is 2r, and here n is 0, that is r minus 1, a0 x raised to 0 plus r, that is x raised to r, plus this quantity but from n equal to 1 to infinity. Same thing here, if I take n equal to 0, I will have r a0 x raised to r. So that I have written here r a0 x raised to r plus this quantity as it is but from n equal to 1 to infinity. So that I have written here. And then this is starting from 1 to infinity, so I have kept it as it is. And here I have to write for n equal to 0, I will have a0 x raised to r. So that is for n equal to 0. We have negative sign, and then this quantity as it is but from n equal to 1 to infinity. So that I have written here, minus a0 x raised to r minus sigma n x raised to n plus r equal to 0. Now here you can see now I can combine all these summations because they are starting from n equal to 1 to infinity. And also we have x raised to n plus r common in each of these summations, and rest of the things have x raised to r common. So I can combine these terms. I can take a0 also common. So I have you can see, if I take a0 x raised to r common, here I will have 2r into r minus 1 a0 x raised to r plus r a0 x raised to r minus 1 and into a0 x raised to r. So that I have written here, and this 2r into r minus 1, that is 2r square minus 2r plus r minus 1 a0 x raised to r. And I have combined all these summations. So I have taken x raised to n plus r common, and I have taken an also common. If I consider the summations with an x raised to n plus r, then I have to combine these three summations, in which I have an x raised to n plus r common. So I have 2 times n plus r minus 1 into an plus n plus r into an, that I have written here, minus an minus 1, so that is here, and minus an. So I have taken x raised to n plus r first common, and then I have taken, or I have combined the terms with an, these three terms. This I can rewrite as 2r square minus r minus 1 a0 x raised to r plus sigma n equal to 1 to infinity. Now I have combined the terms with an, that is 2n plus r minus 1 an plus n plus r an minus, no, here also I have written as it is, minus an minus 1 minus an x raised to n plus r, and I have given this number 2. Now you can see here I have x raised to r power into some coefficient. Here also I have x raised to n plus r into some coefficient, and right hand side is 0. So that 0 I can rewrite as 0 into x raised to r plus sigma 0 into x raised to n plus r n equal to 1 to infinity. This means this is the left hand side and right hand side is 0, that I have written in this way, and we have equality. That means this equality holds if and only if coefficients of like powers of x are same. This identity holds if and only if coefficients of x raised to r and x raised to n plus r are equal. That means here this quantity 2r square minus r minus 1 into a0 must be 0, and this quantity also must be 0, this bracket, it is coefficient of x raised to n plus r. So first I have equated the coefficient of x raised to r to 0, that is 2r square minus r minus 1 a0 equal to 0, and we have assumed that a0 is non-zero, therefore we must have 2r square minus r minus 1 equal to 0, and this is the polynomial equation in r, where r is the exponent r in our solution, which we have assumed in the beginning. So we will solve this polynomial equation in r, and we will obtain the values of r that satisfy this polynomial equation in r, and this equation is known as indicial equation. Remember, this is very important term in the Frobenius method, because Frobenius method depends on the solutions of indicial equation. Now this is quadratic equation in R, so there are three possibilities. We can have two values of R that satisfy this equation. So two possibilities are that R1 and R2 are distinct, and R1 minus R2 is not an integer. Value of difference of R1 and R2 is not an integer. that means we will have some non-integer as the difference of R1 and R2. Second possibility is R1 and R2 are equal, that is we have double root. And third possibility is R1 and R2 are distinct but their difference is an integer, R1 minus R2 equal to some integer value. And in each of these three cases we have different criteria to decide the series solution in this method. So be careful, indicial equation is the main part in the Frobenius method, because depending upon the nature of solution of indicial equation we have these three different categories, and in each category we have different criteria to write down the solution in this Frobenius method. So there are three possibilities: R1 and R2, difference of R1 and R2 is not an integer, R1 and R2 are equal, and difference of R1 and R2 is an integer. Mainly there are two possibilities: R1 and R2 are different and R1 and R2 are equal. But if R1 and R2 are different, then also there are two possibilities, that their difference is not an integer and their difference is an integer, and in each case we are going to have different criteria to write down the Frobenius series solution, and we are going to discuss all these three cases with different examples separately. In this lecture we are going to discuss this first case, in which our solution will be in such a way that difference of R1 and R2 is not an integer. And if R1 and R2 difference of R1 and R2 is not an integer, then how to write down the Frobenius solution, that we are going to discuss in this lecture. Rest of the two cases we will discuss one by one in upcoming lectures. So now we have solved this indicial equation, and we can rewrite this minus r as minus 2r plus r. Then we take 2r common from these two terms and we have r minus 1, and this I can rewrite as 1 into r minus 1. And again I take r minus 1 common, so I have r minus 1 into 2r plus 1 equal to 0. That means r minus 1 equal to 0 and 2r plus 1 equal to 0. This will give me r equal to 1, and this will give me r equal to minus 1 by 2. So both are different and their difference is 1 minus 1 by 2, that is 1 plus 1 by 2, which is 3 by 2, and it is not an integer. So we are in first case, that roots of indicial equation do not differ by an integer, that is r1 minus r2 is not an integer. So here I have two roots of indicial equation, and we can say that roots do not differ by an integer, or in simple words, difference of these two roots is not an integer. Roots do not differ by an integer. Now if roots do not differ by an integer, then we will decide the series solution for each value of r. Remember that our series solution in this form, a n x raised to n plus r, n equal to 0 to infinity. This is the form of our series solution in Frobenius method. So we have to decide values of r and these coefficients a n. Now we have decided two values, r equal to 1 and r equal to minus 1 by 2. So we will replace r by 1 and r by minus 1 by 2, and in both the cases we will decide these coefficients and we will write down the solution in this form. So if roots are distinct and do not differ by an integer, then we have easy case. So now in the next step, our role is to determine the constants an. So for that we have compared coefficients of x raised to n plus r. That means I have to equate this quantity to 0. So that I have done in the next step. Equating the coefficient of x raised to n plus r in 2 to 0, we obtain this equation. And now we can take an common from all these three terms, and we have written 2n plus r minus 1 n plus r an, here minus 1 into n. This is negative, so if we transfer on right hand side, we have an minus 1. Again we can take n plus r common, and we multiply this by 2, that is 2n plus 2r minus 2, and this here I am taking n plus r common, so I will be left with 1, that I have written here, minus 1 into n equal to an minus 1, and here I will have minus 1 now, that is n plus r, 2n plus 2r minus 1, minus 1 into an equal to an minus 1, and therefore an equal to 1 divided by this quantity minus 1 times an minus 1. N is starting from 1 to 3 and so on, because this summation starts from n equal to 1 to infinity. We must have n from starting from 1. So be careful whenever you are comparing coefficients of x raised to n plus r, you check that what is the range of index n in this summation, that you have to write in this relation. This is called recurrence relation between the coefficients. Now we will consider r equal to 1 first, and using that value of r, we will determine the constants an, and we will write down the corresponding solution, and then we will put r equal to minus 1 by 2. Again we will determine the coefficients an, and then we will write down the second solution. So first I am writing for r equal to 1, that is first solution using r equal to 1. So here I am taking r equal to 1, and I will have n plus 1, 2n plus 2 minus 1, that is 2n plus 1 minus 1 into an minus 1, and of course n is starting from 1 to 3 and so on. And this I have multiplied these two, n into 2n, that is 2n square plus 3n, n into 2n, that is 2n square, plus n plus 2n, that is 3n, and 1 into 1 plus 1 minus 1. So I have 2n square plus 3n only. I can take n common, and I will have n into 2n plus 3, an minus 1, n takes the values 1 to 3 and so on. Now you can see, if I take n equal to 1 here, I will have a1 equal to 1 into 5 into a0. Now suppose I have not taken a0 as non-zero in my solution. I have started by assuming that our solution is in this form, an x raised to n plus r with a0 non-zero. But suppose a0 equal to 0, then I will obtain a1 equal to 0. Then a2 will depend on a1, so I will obtain a2 equal to 0. In short, if I consider a0 equal to 0, then an will be 0 for all n, and our solution will be trivial, that is y equal to 0. And we are interested in non-trivial solution, therefore we have taken a0 as non-zero real number in the starting point of our solution. So whenever we start with our Frobenius method, we will assume our solution in this form, and with the assumption that a0 is not equal to 0. So now I have obtained few of the coefficients by taking n equal to 1, 2, 3. For n equal to 1, I obtain a1 equal to 1 over 1 into 5 into a0. For n equal to 2, I have 2 into 2, 4 plus 3, 7. And for n equal to 1, I have a1. And then I have put value of a1. So I have 1, 5, 2, 7 into a0. Then for n equal to 3 I will have 3 and 2 into 3 6 plus 3 9 into a2. So that I have written here. Again I have substituted this value of a2 here and I obtain this expression for a3. Similarly I have obtained value of a4 and then I have written the first solution. The first solution I have denoted by y1 and our solution is in this form: sigma a n x raised to n plus r, n equal to 0 to infinity, and this I am writing for r equal to 1. So here I have taken r equal to 1 and I can write few of the terms of this solution. If I take n equal to 0 I have a0x, for n equal to 1 I have a1x square, a2x cube and so on, and then I have put these constants here a1, a2, a3, a4 that I have put in this solution, and then I have simplified. I have taken product of all these quantities and I derive this series solution. y1 equal to a0 times x plus x square by 5 plus x cube by 70 plus x raised to 4 by 1890. This is the solution corresponding to first root, say r equal to 1 of initial equation. Similarly, I have to write another solution for another value of r which is minus 1 by 2. So that also I have done. I have taken r equal to minus 1 by 2 in this equation. Then I have obtained values of coefficients and then I have written the solution corresponding to r equal to minus 1 by 2. So that is second solution using r equal to minus 1 by 2. If we take r equal to minus 1 by 2 in number 3, that is in recurrence relation, here I have taken r equal to minus 1 by 2. So I have n minus 1 by 2, 2n plus 2 into minus 1 by 2, that is you can see 2n plus 2 into minus 1 by 2, that is minus 1, and minus 1, that is 2n minus 2 and minus 1. So that I have written here 2n minus 1, that is 2n minus 2 minus 1. Here also n starts from 1 to infinity. Then I have taken product of these two quantities and I obtain this quantity. So 1 will cancel out and here also I have n into 2n minus 3 an minus 1. Then I have written few coefficients for different values of n. For n equal to 1 I have 1 into 2 minus 3, that is minus 1, into a0, that is minus a0. For n equal to 2 I have 2 into 4 minus 3, that is 1, into a1, and value of a1 is minus a0, that I have written here. For n equal to 3 I have 3 into 2 into 3 6 minus 3, 3 into 3 into a2, and then value of a2 is minus 1 by 2 a0 and I obtain minus 1 by 18 a0. For n equal to 4 also I have calculated, and finally our second solution is an x raised to n plus r, r is minus 1 by 2, and for I have written few of the terms of this series. For n equal to 0 I have a0 x raised to minus 1 by 2 plus a1 x raised to 1 by 2 for n equal to 1. For n equal to 2 I have a2 x raised to 2 minus 1 by 2, that is x raised to 3 by 2. For n equal to 3 I will have 3 into 2 6 minus 1 5 by 2, and then I have put values of a0, a1, a2, a3 in this form, and this is the second solution corresponding to r equal to minus 1 by 2. Now general solution is given by y equal to c1 into y1 plus c2 into y2. We can observe that these two solutions y1 and y2 are linearly independent. Here terms are x plus x square and so on, and here terms are x raised to minus 1 by 2 and so on. Linearly independent means we cannot write y1 as constant multiple of 2 or we cannot write y2 as constant multiple of y1, or we can say that if ratio of y1 and y2 is constant, then y1 and y2 are dependent. But here ratio of y1 and y2 cannot be constant. That means y1 and y2 are linearly independent solutions, and therefore we can write the general solution as linear combination of y1 and y2. So I have put values of y1 and y2 here, which I have obtained. Here a0 is arbitrary constant, so if you wish you can select particular value for a0. You can choose a0 equal to 1, and or you can combine these two as single constant. You can put c1 into a0 equal to say capital A, c2 into a0 equal to say capital B, and you will have a into y1 plus b into y2, and this is the general solution of given differential equation. So this is very big problem, but be careful. You have to start by showing that x equal to 0 is a regular singular point of given differential equation. Therefore Frobenius method can be applied, and series solution is in this form: n equal to 0 to infinity an x raised to n plus r. Then you find out values of y dash, y double dash, substitute them into given equation. Then you find out coefficients of like powers of x. Here we have compared coefficients of x raised to r and x raised to n plus r, and by comparing the coefficients of x raised to r, we obtain indicial equation, that is quadratic equation in variable r, and it has two roots, say r1 and r2. In this case r1 and r2 are different, and their difference is not an integer. Therefore we have obtained solutions corresponding to r1 and r2 by taking r equal to r1 and r equal to r2 in this form. For r equal to r1 we have this form, and x raised to n plus r2 for r equal to r2. If roots of indicial equation do not differ by an integer, then our Frobenius series solution will be in this form. If roots are equal or difference of roots is an integer, then we have different criteria to write down this second solution, but first solution will always be in this form. And be careful while doing all these calculations, because there are chances of mistake. So be careful, and if you can go by patience, you will definitely be able to write down your solution. So this is all about this session. I hope you like it. If you have any doubts, you can ask in the comment section. Thanks for watching.